welcome, because then Sophie can answer as well.
Luca is here also.
I didn't see the name, but
so wait here. You know, okay. In what kind of let's say open waveguide situation would you find this node? So now let's imagine that you stretch laterally, you know, your wave channel. So now it becomes the ocean, you know, but somewhere you have this kind of situation, I don't know, in the landscape where perhaps it can be the depth actually. It doesn't have to be, you know, it could be the depth. At some point you have a big hole and the depth is in the, so this could exist, you know, maybe this kind of phenomena exists in OpenSea.
You mean so all the example I have shown is when it is possible to see two disjoint domain in space, one domain where it will be incident, one domain where it will be transmitted. That is the basis of all, because you have to be able to put ingoing on one side and outgoing on the other side.
Yeah, but you just need to have a jump in depth, you know, and you have your two domains. Even in OpenSea, you have a jump in depth. Left, right is not the same depth, and that's your geometry. You know, it's the same. I mean, you know it. You can report the change of geometry in the depth.
No, but you are talking about a 1D problem.
No, 2D.
No, but from above, it is just like a slab in with an incident wave with some angle. Yeah, so yes, it can be done because it is separable problem. What would be difficult is, let's say, cylinder in 2D space, for instance, because you cannot separate ingoing domain from outgoing domain. You see what I mean? Because an incoming wave from everywhere around.
Yeah, I see.
You cannot have two different domains in space.
And this phenomenon of perfect transmission, so that you have unveiled here, would allow you to revisit some of the work, you know, by, I know it might look quite remote by Ebesen and so on.
Yeah, I think the list I was listing at the beginning, different domain where transmission is at stake. Yes, we could take one by one and apply this reflectionless mode because it has not been done. So it's a new tool. So, for instance, for the transmission eigenchannel through disordered media, we are planning to do that with Mathieu Davy, also for this diffuse regime of wave, to see how it's playing the symmetry, for instance, because the PT symmetry, as we have seen, is able to aggregate the good transmission along the real axis. So that's why most of the time people working on perfect transmission, they were taking mirror symmetric situation because it is a much better candidate. But after even breaking the symmetry, it's possible to play because, let's say, since eventually the reflectionless mode, is that cavity problem here with gain on one side and loss on the other side. Let's say that you have a complex eigenfrequency that is not real. Then after you can play on incoming or outgoing in the sense of reducing gain or reducing loss. For instance, taking smaller waveguide on one side, and then you know in what direction you will go. So it's possible to tune. That's but this kind of tuning, it was more by the way the subject of the last reference I was citing.
And the obvious question, I mean the naive question again is, so what happens if you replace the Helmholtz operator by Navier? So now you have this coupled. Well, you have, you've worked on this. You have this in-plane coupled pressure and shear. Anyway, they couple at the boundaries. So you have stress-free boundaries.
You mean lump wave?
Yeah. They are in plane. So yeah.
After, I would say it will be strictly exactly the same problem as to compute QNM.
Yeah.
Okay, so to compute QNM for lump waves, we know that it's not so easy because it's difficult to apply QNM in vectorial elastic waveguide.
Okay.
And since there is a a challenge to compute QNM, there is as well a challenge to compute this reflectionless mode.
Okay. Okay. At some point, just for our recollection, you've got these exceptional points. So it's in one of your slides.
Yeah.
You mentioned them in passing.
Yeah, but because in fact, yes. So here, for instance.
Yeah.
So the complex reflectionless mode frequency are in red. It is a non-Hermitian problem. And then when there is a degeneracy of two eigenvalues here, so when these two eigenvalues are coalescing, it corresponds to an exceptional point of the reflectionless operator. Because this operator is non-Hermitian, meaning that when these two eigenvalues are coalescing, we have a Jordan block problem, and we lose one dimension in the eigenmodes. So it is an degeneracy going to exceptional point, in contrast to degeneracy in Hermitian problem, where it's just you keep two independent eigenvector. Here, when the two guys are coalescing, you have the two eigenvectors that are parallel, and it is an exceptional point. So it is funny because in fact, yes, you have an exceptional point in a problem that initially is lossless, because you take a scattering problem, it's this slab Fabry-Perot, there is no loss. But playing with the ingoing, outgoing, you make it non-Hermitian, and then you have this coalescence of perfect transmission that correspond to exceptional point of the reflectionless operator.
So it would be nice if other people can ask questions.
Yeah, Mohamed.
I mean, they can be more advanced, less naive, Vincent is very happy to be challenged by some people, even if you want to bring in some controversy to have a bit of fun. You're welcome. It's always good to test Vincent. He likes it.
If it's too challenging, I will pass the question to Anne-Sophie. Anyway, I have a joker.
We particularly welcome young researchers because it's also an opportunity to, engage, a possible collaboration with Vincent if you come up with an interesting problem he did not think of. Alexei, do you have a question?
I cannot think of one just yet. Good to see you guys.
Hi, how are you?
I'm all right. As usual. Lots of teaching, as for all of us, But anyway, it's quite interesting, and I think what was very unexpected from my perspective is when you change the abrupt connection in the waveguide to a smooth connection in the waveguide to find a lot more modes gradually forming, perfect reflection, I suppose, once it gets completely smooth, i.e. perfectly smooth. So I think this is a very nice physical illustration of how you go from very abrupt to very smooth.
Yeah, it seems that it's, yeah. it's able to attract many, let's say, going continuously from abrupt to smooth. I suspect that there would be a lot of eigenvalue coming from far away and aggregating in this frequency range, I guess.
I don't think I've seen this kind of clear illustration how you transform from one kind of spectrum to another.
Yeah.
Very nice, but I think it's just a lot to think just to get your head around it.
Yeah, it's true. A lot remains to be done.
So people, any more question? It could be from the physical, engineering, or perhaps applied mathematics point of view, depending upon your background.
Maybe Jan from Lille.
Yeah, great.
Yeah. Okay. So thank you very much for a very nice talk. So at the end of the talk, during the video, it seems that most of the energy is doing confined inside the upper size corner of the cavity. Is there an explanation on that, or is it something expected? So you can see all the energy, or is it maybe a defect? I don't know exactly what does it mean.
So you mean that here we will see on the diagonal kind of node on the diagonal, yes?
Yeah.
Yeah, I think that it is because when we tune the cavity size to get this zero transmission, after we know that the modes, the wave inside the cavity has to be unable to leak. And so naturally the wave equation is choosing wave field inside the cavity that is with this low amplitude at the exit. It is kind of overlap argument, because after we can always think a little bit like that. Modes that are able to be trapped, it's because they don't have the ability to leak, and they are not able to leak usually because they have a low amplitude where is the exit.
Okay.
I think that's the mechanism. And after, it's really interesting to apply this kind of effective cavity to get it explicitly right.
And the shape of the cavity is also something important in this way to change this mode or not?
Let's say so. There it is. How to say conjecture? Yes, conjecture. It has to be large enough in order for, because here in the lead at right and left, the propagation is essentially 1D. It is plane wave propagation on both sides. And then to be able to have a transmission coefficient 0 for this positive imaginary frequency, really, my conjecture would be that the cavity has to be large enough in order that the wave is really 2D inside the cavity. For instance, if you take a cavity that is narrow, so meaning like a chimney, it will be impossible to get this zero transmission at the positive imaginary part of frequency. So it has to be, let's say, yes, the shape is important because the wave has to be really 2D. Full 2D.
Okay.
But it's just a conjecture. Not yet found how to make it clear.
And in the 3D systems, we can imagine that it's a square, or not a square, but a cube or something like that. Or
I guess it would be the same in with a box, 3D box, a cube. Important is that the cavity is more than 1D.
Okay. Okay. Thank you. Thanks again.
Now, I have a question also concerning the results in the with some periodicity that you have shown in 1D.
Yes.
I heard that something was proved and then was not proved. I don't know exactly what is observed and what is proved concerning the fact that there is a.
I have chosen this example because okay, so I was playing with the perturbation of the Fabry-Perot, and then I thought about by the way, if we take a finite periodic system in 1D composed of an integer number of cells, n, if you take n cells, automatically in 1D, we know that there will be at least n-1 perfect transmission. And then I was choosing that one because it breaks the PT symmetry. And at the same time, I knew that it had to keep some perfect transmission. So it is what we see. We have 4 cells, and we see that by team of 3, we have this n-1 perfect transmission. But after, what remains open is how to relate that with this non-PT symmetric operator. Because it is non-PT symmetric, so there is no reason why it should be like that from starting from PT symmetry operator argument, from operator argument, from reflectionless mode argument. It's an open question to understand why this is able to keep this real eigenvalue.
And do you expect something similar in 2D with some periodicity inside the perturbation?
For sure, yes, for sure, as long as the propagation is mainly monomode. So there will be maybe a little bit of near field effect, but it will not change this n-1 rule.
Okay.
And here, what is different also from the PT symmetric perturbation is that when we look at the reflectionless versus QNM, you see that the reflectionless is bringing just 1 QNM instead of 2 in the PT symmetric. So it's a different behavior.
I noticed that also.
So it's, yes, it's very new. It's from 2 days ago.
Thank you.
Okay, so do we have any other questions? It could come also, like I said, from the engineering side.
Oh,
it doesn't. Yeah. Hello. Yes.
hello. I have a question. Is there a way to compensate the phase delay because of the obstacle in the waveguide? Hello?
Yeah.
Hi, Kun.
Yes. For when it is monomodal, I guess it shouldn't be so difficult with adding some resonator that can be tuned easily for with just 1 degree of freedom in the wave, it shouldn't be so difficult. After, when it becomes multimodal, I have no idea. So here, for instance, so it's a question of degrees of freedom, how to play, to be able to be, so adding another apparatus behind, and after, yes, it's a question of number of degrees of freedom. I have no idea for this multimodal. For the monomodal, I guess shouldn't be so difficult. But when it goes to multimodal incident wave like that, I don't know, really. It's a question of degrees of freedom. So we would need resonator and enough parameter to tune everything. Yes.
Okay, maybe for example, in some special case that you can have some multiple 2π, so you can tune it.
Yeah. Yes. And after as well, let's say if you have this kind of geometry, so it is symmetric, and you know that just keeping the symmetry of the obstacle, but changing the geometry, you will keep the reflectionless mode, and you will change the phase. So you can play on that maybe, because this phase, so you still have reflectionless situation, but you will change the phase of the outgoing wave. So that could be a way, maybe.
Okay, thank you.
So do we have a couple more questions from young or more senior researchers? We would really like to close this webinar with one or two more questions.
Question.
Yeah?
Yes, there's also Kun here. Thanks for the nice talk. I have maybe an open question that I see you have some, if you modulate the reflective index periodically, but in experiment, you only show cavity. If you replace your cavity by a crystal line, then with a source with increasing power, then do you still can see the band gaps or the exceptional points not a photonic crystal, maybe water wave crystals? It's quite open that if you replace the cavity by
it's related to the 1D or the 2D?
Let us talk about the 1D first, I think.
Yeah, this one, for instance.
Yes, you have the band gaps here. Yeah.
Yes, and sorry, I didn't get the.
In the experiment, shining a wave with increasing power as the complex omega source. If I understand you.
Yeah, in the water wave now. Yes.
Yes. Then, if you have this kind of increasing power of source, you still see the band gap of this kind in the water wave experiment. Because I'm thinking of this that for conventional crystal, you have a band gap. But it is symmetric. You can close the gap by producing the exception point as mentioned. Then inside the complex K gap, you have two branches, one increasing, one decreasing. Then you have an increasing power. So I'm thinking that, do you have, in the experiment, you see the increasing branch or the decreasing branch, or do you see both of them? This is why I'm asking this question.
Yeah, I think it's an open question, yes.
Yeah, so this is quite open. I know. It's because you done a nice experiment by a cavity. So I'm thinking that if you replace the cavity by a periodical system, then normally a water wave crystal, what's the result of it? It's quite open. Because normally in physics, I'm doing physics, whatever the complex omega band structure or complex K band structures, complex omega, we always fix the K as real. For the complex K, we always fix omega as real. For fix the omega as a complex number to find a solution in the complex K plane. Yeah, I'm asking that the physics, the scattering result of your system. This is quite open.
Yeah, it might be interesting. It's true.
Yeah. Okay, thanks.
So perhaps another open question? Like the previous one, we really welcome these kinds of, open questions. It's very good to,
yeah, of course,
challenge Vincent a little bit. We can learn from him today, on a very nice topic. And of course, Vincent will be more than happy to answer any questions you would have by email. So
totally.
I see that we have some friends who are experts on PT symmetry, and if one of them would like to ask just a very last question, a more theoretical one to close the webinar? No? Hello, hello. Well, so shall we speak, shall we thank our speaker again for this really nice talk, which was, in my opinion, very pedagogical, and I'm very pleased I've learned a little bit in this exciting topic.
Thank you, Vincent.
Thank you. Thanks a lot.
Thank you.
So next week we are back to photonics, if I'm not mistaken, Bogdan.
Next week.
It's Oliver Wright, I think,
yes,
next week, who will give a talk which will be very much photonics oriented. And Oliver is a fantastic lecturer who also loves to, popularize the science. So I really encourage people to attend also next week webinar. So thank you very much for your attention. And once again, if you would like to get in touch with Vincent afterwards, please do not hesitate to drop him an email. Bye-bye and stay safe.
Thank you. Have a good evening. Bye.
Thank you very much.
Bye.
Bye.